is geometric. Okay? This always, if these are the same, it seems geometric. So, in this, if I were to look at the ratio of A2 to A1 in the second series, what's the ratio of A2 to A1? Look at the sign in front, by the way. Negative 3/8 to positive 3/4 is negative 1/2. What about the ratio of 3 to 2? 3/16 to negative 3/8 is negative 1/2. They're the same, it seems like geometric. Although, I guess it could take a turn for different later, but it seems on the face like geometric. Are you with me so far? Okay. If you try the next two then and verify they are geometric, please, and then we'll move on to the next. Hi. Thank you. Okay. What about the third one? Common ratio, yay or nay? No, they do not turn out the same. So we would conclude that that is not geometric. And the last one, well, we could generate a term or two. What's the first term? Is it 1 over 3, negative 1 over 3? 1/3. The second term? Negative 1/9. Third term? Positive 1/27. What's the common ratio each time here? What am I multiplying by each time? Negative 1/3 each time. Now, the point then is, if you see summation or anything with an exponential, this constant, a constant to a variable exponent or an increasing exponent, this is geometric. And the number in here, the C, is the common ratio. In fact, I should call it, rather than C, I should call it. So then, if you get a case, yes, ma'am, sorry.
I understand for the third one.
Yeah.
So I think it says like A0 or A2.
Yes.
So why the
I was just kind of reducing it. It's 6/8, but it reduces to 3/4. I probably should have. I just thought it would simplify easier, but it was 6/8. Okay, sorry about that. You're right. It didn't let. It was like if then you see a series with an exponential, then these are geometric. I didn't really like the way this read in the last class, so I'm just going to say, would you write down here, these are geometric. In this case, the common ratio is -2. In this case, the common ratio is negative 3/4. Okay, but they are both geometric because you're multiplying by the same thing over and over. Or if you took any term to the one before it, it's always the same ratio. All right, now, I don't want to overthink it here. Let's talk then, what about, do these add to something and what do they add to? Let's look at this previous case. This is geometric, I said. Does this approach a finite? Yep. Yep.
So for the fourth one on the like top or whatever, yeah. So you said that when C is raised to the n,
Uh-huh.
the C is the ratio.
Yep.
And so does it matter if it's the same n because -1 to the n plus 1 and the 3 to the n still have the same n?
I agree. If you can make it like this, then you're golden. I could make this fit the pattern by rewriting it. And this then says, yep. So the exponents being different is not a huge sticking point. I can make that work. Okay, that's a good question. All right, so going to summing these. Sorry, this. If I add infinitely many of these terms, converge or diverge? Diverge. If I were to graph the partial sums, what would the graph of the partial sums look like? The first partial sum is, which is to say the sum of the first one terms is 4. The sum of the first two terms is -4. The sum of the first three terms is -4 plus 16, 12. The sum of the first four terms is 12 minus 32, so -20. So, does this series converge to a finite sum? Obviously no. This, however, or maybe a better example would be this. If I look at this series, first of all, do you think it's geometric? Yes, you're multiplying by half each time, yeah? If I were to look at the partial sums, in fact, let's just do this, ignore the half right now. What's the first partial sum? 1/2. The second partial sum? 3/4. The third partial sum? 6/8 plus 1/8, 7/8. The fourth partial sum? 15/16. Does that seem like it's growing out of control or starting to approach a limit? Approaching a limit of 1. So it feels like geometric is a bit of a mixed bag. This one was geometric, but it diverged in some. That one's geometric, but it converges in some. And so it seems like there's a case or cases where it does. What's the case? When does it converge and when does it not? Remember, we talked yesterday about it. You're only going to add infinitely many things if the terms get smaller and smaller and smaller, right? You can't add infinitely many things when they're getting bigger and bigger, because that'll go out of control. But if the terms are decaying, like they are here, then you've got a chance. Well, in geometric, what makes the terms decay? A fraction. Do you mean so like 10/3?
Fraction where the denominator is growing bigger.
Okay, so we would say that is where the common ratio is less than 1. Well, I'm actually a little bit confused. What was the common ratio here? -2. Isn't that less than 1?
Between 0 and 1.
Between 0 and 1? 2 is strict.
Oh. -1.
-1 and 1. Now you will. Okay. If the common ratio is basically going to cause the parts to get small, positively or negatively, then it must be a case that you're multiplying by something between -1 and 1. Typically, this is the way you start, but the more common is to say the absolute value of r is less than 1. Not equal to. Yes?
Okay, why not equal to? Because if it's equal to, then it would be just a line.
So consider this. What if you had a geometric, what if you just started with whatever? Say the first term was 1. Actually, I'll start it with 2. If the common ratio is 1, what's the next term? 2. And what's the next? Yeah, it's got to get smaller, and it's got to be less than 1. All right. Now then, I'm kind of diverging from my notes because as I taught last period, I didn't like how they were rolling. I think it was not good. Say you looked at this series, 1/2 plus 1/4 plus 1/8 plus 1/16. Now we know in our mind that it's approaching 1, right? The question is, can you prove it's not approaching 1? It is 1. I can prove that it is 1. How can you prove that it is 1? Remember how? All right. Fight infiniteness with infiniteness. So I would like you to make a series that will fight that one infinitely also. Now, let's say I said, all right, forget you, I'm going to subtract s. Then it would be -1/2, -1/4, -1/8. Now, that's great, but it doesn't really get me anywhere. It doesn't really prove that's a half. So that didn't get me anywhere. Instead, I would like to get a little bit of a shift. So I'm going to take this series and multiply it by -1/2. Now, if I multiply that series by -1/2, then I'm going to multiply the right side of it. What's 1/2 times -1/2? -1/4. What's 1/4 times -1/2? -1/8. 1/8 times -1/8 is -1/16, and so on. Now, if fundamental rule of math is if I have two equations that are true, I can add them to get a third equation that's true.
1/2 S is 1/2.
Yeah, 1/2 S implies 1/2, therefore S is, must be 1. Now this is how you prove many things happen. For example, what's 0.1 repeating as a fraction? 1/9. What's 0.2 repeating as a fraction? 2/9. 0.3 repeating as a fraction? 3/9. I think you see where I'm headed. What's 0.7 repeating? 0.8 repeating? And 0.9 repeating is? Yeah? Okay. Must be 1. 9 forever is 1. All right. Now then, this is how you are going to develop a general formula. What if I wanted a formula for any geometric series? Okay? Think generally. Now, this is great, but it's not very useful to work with. So I'm going to rewrite this as A1.
Wait, I don't understand.
What?
I'm sorry, I'm so confused.
That's okay.
I don't understand why that is, and I still don't think I understand even why 0.1111 is 1/9.
Oh, it's because if you divide 9 into 1, that's what you...
Do you agree that 0.3 repeating is 1/3?
Yeah, I guess maybe I should
Yeah, I agree that, but then I don't
That's-
understand why 0.99999 forever is 1.
Well, that is to say that if I divide 1 into 1, then it's 0.9.
No, that's what.
That's not true. It's
Well, of
1.
course it is. No, it's true.
No, it's not.
Of course it is. I can prove that 0.9 forever is 1.
How can
Do you, all right, do you agree that this is equal to this? This, do you agree that that is true?
Yeah, there was a
Yes.
Right?
No.
You don't?
Okay, I can kind of see like
This goes forever.
it gets to like such a small like
Yeah.
Actually, I'll go here. I will prove that this is true. I understand that this is not yet true, okay?
Okay.
It's okay, but I will get you into a point where you cannot disagree, all right?
Okay.
Stick with me. Do you agree that I could multiply both sides by -0.1? If I multiply both sides by -0.1, actually, I'll just say -10. Okay, now, I did it to both sides, so it's all good. You agree? My new equation is -9 minus 0.9 minus 0.09, forevermore equals -10, yeah? All right, now you agreed with equation 1. And you agree with equation 2, yes?
Yeah.
Okay. Now, do you also agree that a fundamental rule of math is if two equations that are true are added, you get a third equation that's true? So I'm going to add these two equations. And when I add equation 1 and 2, I get 9. Oh, actually, sorry, -9, thank you. -9. Gone. gone, forever gone, equals, what's negative, or sorry, 1 minus 10? Negative 9. Do you agree that's true? There you go. Isn't it funny? Okay, no, this is, it's with this kind of logic you can prove that an A is an F. I think I did that last time. I did that for you guys. I mean, you could prove to your dad that, hey, I know I have a 40% in the class, but it's really an A.
What?
I do not remember.
Wait,
doing
look at that. No,
Okay, I will prove that your 55% is actually 90%. Okay?
wait, I gotta write this down for my
Of course
dad.
it is. You ready? Sure. Okay. Do you agree that 55 is equal to 55 plus a lot of zeros?
Yes.
Ed? Do you also agree that 0 is
I'd rather review what has to be done from themselves.
45 minus 45?
Yes.
Ed? Do you also agree that because there's nothing outside those parentheses, I can drop them? Okay.
Oh, well, yeah, because there's always a plus or cover, always a
Ed?
plus.
Do you also agree that if I felt like it, I could put parentheses around these?
Oh, yeah, I've seen the same.
And then after the 0, it's there's a 1 without, 1 minus 1.
Therefore, 90 equals
1, 0, and 1.
true. There you go. So now your A is an F, just like that. Okay. Back to the lesson. Where? You mean at the end of this?
Yeah, like,
At the end of it?
55 plus 45 is not 90.
Who's to say? I could actually make the that true too. You're right. 35 we should already be. Wow. You have the theory, right? Yeah, who is right?
So, Mr. Lincoln, what is wrong with all of this?
All right,
It
well,
obviously is flawed.
rules of math do not allow you to insert and remove parentheses. So you can't. Okay.
Wait, why though?
Because otherwise, math breaks.
Well, okay,
It's enough.
down there you have your plus 45, like that.
These go forever.
Yeah, so we're going to eventually have to have
Eventually?
negative.
Eventually, you can after forever.
Yeah.
Just after forever.
There's another
All right, back to the lesson. So, this idea of finite, developing an actual sum, for instance, something that is infinitely long, can be done in the abstract to get a formula that works in all cases. So that's where we're headed. Let this be a geometric series. Now, A1, A2, A3 is not very helpful because it really doesn't even have any issue about geometric in there. So on the first stage I'm going to do is rewrite this as geometric. If this is geometric, then A2 should be the result of taking A1 and multiplying it by R. And A3 would be to take A2 and multiply it by R, which would be like A1 times R twice, right? And A4, if I were so inclined, would be like A1 times R 3 times over to get to the fourth term. You with me so far? All right, that goes forever. Now, I'll call that equation 1. In developing a formula, you try and get rid of the infiniteness with another series like it but not the same. So in developing equation 2 that I'll add to this one, I first will need a negative to get subtraction going. And I'll need a little bit of a shift over. I multiplied here by negative 1/2, but that was only because the common ratio was 1/2. So here I'm going to multiply equation 1 by negative r. If I multiply by negative r, then the left side is s times negative r, or negative rs. A1 times negative r is negative A1r. A1r times negative r is negative A1r squared, and so on. In other words, I get a shift over of 1r power. And again, I remind you, this is infinite, so it's not like the bottom one has one past the other one hanging out there. There is no past, infinite. If I add those two equations, 1 and 2, then the left side, s minus rs, I'll deal with in a minute. But the right-hand side, what is it? Just A1, okay?
S is A1.
So s is A1 over 1 minus r. Now, in the end then, if you have identified that it's a geometric series, first, an infinite geometric series converges only if the terms are getting small. And that happens because what you're multiplying by is between negative 1 and 1. Otherwise, it diverges. If the series converges, then the sum is A1 over 1 minus r, again, only if r is less than, the absolute value of r is less than 1. It's imperative that you check that first. Write yourself a note. Check first for r less than 1. Else, you're going to be the dummy that says 1 plus 2 plus 4 plus 8 plus 16 is negative 1 or something. Foolishness, okay? Do you agree that's geometric?
Yes.
Okay? And if you mindlessly plow ahead with the formula, then you'll say something like 1 over 1 minus 2. You're going to tell me that that sum of infinitely many positive numbers equals negative 1. That's ridiculous. Okay? It's because this gets converged. You should not even be using the formula. Okay? Okay. So, say this. I'm telling you that all geometric, you don't even have to check. What's the common ratio? 3. So the sum is not applicable, or if you like, you could say it's infinite. Okay? It does not converge. You are not to use the formula. Do not try and find the sum. The sum is infinitely large. Okay? What's the common ratio here, or more importantly, the absolute value of the common ratio? Negative 3 halves. That is not less than 1. So again, not applicable. That sum would spiral out of control, positive and negative infinity divergent. Okay? What about here? What's the common ratio? 2/3. So that front 2 doesn't really affect the common ratio?
No.
That's correct. It does not affect the common ratio. Does it affect A1? It is, in fact, going to have to do with A1. It does converge, so we can find the sum. A1 over 1 minus r. What is A1? Please pay very close attention. Not 4/3. Pay more attention. Starts at 3. So it's actually 16/27. It starts at 3 here. Careful. What's the common ratio? 2/3. So this then amounts to, this is a 16 out of 11. 16/27 over 1/3, or 16/27 times 3 over 1. The sum is 16. Yes?
Did you say that the front 2 does affect A1? Actually, that's not
It does affect A1 in that it goes into A1, but it's not A1 alone. It's a part of it. It goes into it. Okay? This bad boy, what's the common ratio? Negative x. Now that could converge for x's that are between negative 1 and 1. So let's say it did converge. Instead of getting a numerical answer, I'm actually going to get a function answer. What is the common ratio? 1 over 1 plus x. Now that's actually kind of cool. If you were to pick up your graphing calculator and graph this and graph that, They would be the same within the radius of convergence. They would model each other pretty well within a region. We'll talk about that later. Yes? You don't. It kind of depends on what x is. This would converge if x was defined as a value between -1 and 1, but if x is greater, then you wouldn't. So it converges if under this condition. Okay? We'll get more to that later. I'm trying to get that in a little ahead of time so you're familiar. All right, go to the back side. This was an Algebra 2 problem, but we're going to do this in an Algebra 1E kind of way. Are you ready? Not Algebra 1E, sorry, Calculus. It is 234 over 999. Okay, so as an infinite series, it might help to expand this. Okay? That's an S.
I don't know if it's integral not wrong.
It's an S. Okay. That is a geometric series because if you break it up into the sum of all those 2, 3, 4s, then you start to see the sum of a pattern, right? Which makes it a series. Is there a common ratio? Is there something you're constantly multiplying by each time to get the next term? 1 over 1,000, right? Do you agree? Or 0.001? Okay, now if the sum then, actually, I think you'll agree that is less than 1. It converges. So it's applicable to use the formula. We can use the formula, or appropriate to use the formula. What is A1 in the pattern? 0.234. The common ratio is 1,000, yeah? That is then 0.234 over 0.999, which is, if we divide or multiply by 1,000 top and bottom, 234 over 999.
Why isn't it?
Why is it?
Yeah, because 1 over 900 is 0.000 or 0.001.
What?
1 over. Why isn't it 234 over 900? 1
What's 1 minus 1,000? I don't see an error.
I think one more zero. He's gonna confuse with that. No, I use.
Oh wait, no.
What? Oh, okay.
I remember something.
Oh, okay. Cool. Don't use that. All right. In the interest of time, let's go to telescoping, which is less familiar. So, if you would, consider what the first 4 terms of this would be. When you put in 1, you get, actually it'll be really like 8 terms because you're going to put in 1 through 4, and each time you're getting in 2 terms. So you're going to get something like 1 over 1 minus 1 over 2 when you put n of 1 in. Then you'd have 1 over 2 minus 1 over 3 when you put n equals 2 in. Then 1/3 minus 1/4, and 1/4 minus 1/5. And then students want this, but we just start slashing. And okay, exactly. Say what? That's not. You can see that it's going to start to collapse on itself. You have a -1/2, +1/2, 1/3, -1/3, so on. So I'll get to that in a minute, but I'm going to unfortunately make you do this a little more out here because they're going to get harder, and I need you to have a little longer method for when they get harder. Okay? So the first 4 partial sums. What is the first partial sum unsimplified? Unsimplified. Okay. S2, partially simplified. 1 minus 1/3, okay? I slashed the 1/2, but I'm not gonna combine the 1 and a third. I don't need to. I wanna see a pattern. I don't want them together, okay?
So S3 is
Okay.
S.4.
So for those whoever said they don't get it, S2 is those two, do you see? You also see that the halves will go away.
Oh, I see.
So what is S3? 1 minus 1/4. The halves and the thirds go away. Okay, now, the very definition of converging is if the partial sums converge. So what you're now going to do is write a formula for any partial sum. Look at the pattern here. The first partial sum is 1 minus 1 over 2. The second partial sum is 1 minus 1 over 3. The nth partial sum is 1 minus 1 over n plus 1. Wouldn't you agree this denominator is 1 more than the index? Right? All right? So if we did infinitely many terms, then the true infinite sum is what the partial sums approach as you go on and on and on. Well, as you go on and on and on, it becomes 1 minus a billion, 1 minus a trillion, and therefore it approaches. Okay? They collapse to 1. All right. Now, because of that collapsing nature, that's why they call it telescoping. Call this one. This is an issue I don't want to get into, and actually, I'm not even sure if it converges. Will you change this one to 1? Okay. I'll do one more together, and you'll try 3 on your own. So, my goal is to show, not find what it converges to, but show that it converges to what you say it does. Start, if necessary, by writing some terms. 1 over 2 minus 1 over 3 for the first pair, plus 1 over 3 minus 1 over 4 for the second pair. Then, again, if necessary, write some partial sums. 1/2 minus a third is the first partial sum. The second partial sum is 1/2 minus a fourth. Okay? Now here's where it's required. I require you to write the nth partial sum formula. What is the nth partial sum formula? 1/2 minus 1 over n plus 2. And it's required then that you show that infinite sum is the limit of the partial sums, or what the partial sums approach as n gets infinitely large. As n gets infinitely large, it approaches 1/2. These two are required. The others, maybe as you do more and more of these, they'll be less and less necessary. But for now, I'd suggest you show a few terms to look at. Try the next 3 then on your own. I can tell you the fourth one is a bit of a home demon, but we'll talk about it in a minute. If you persevere on the fourth one, you'll see.
The third one doesn't. It has here, but okay, the pattern is 1 plus 1 over n plus 1. Oh. First set. 1 plus 1. Second set. S hat plus 1.
Yeah, you can't do it.
Oh, that's plus one. So you actually have those ones that you're interested in. Third plus 1.
Gosh, I'm so stupid.
Yeah.
Give it so like,
I really.
Yes.
oh, wait, never mind.
For the second one, do you agree with the partial sum formula 1/3 minus 1 over n plus 3?
Yeah.
Do you also agree that that converges to 1/3? Okay, cool. For the next one, did you see a problem?
Yes.
What is the problem? It's add, yeah. So if there are no negatives, then it is not telescoping. It will not collapse. Okay, the whole idea of telescoping is that you have a positive and a negative version of the same number. If they're all positive, you have no subtraction. It's just adding in three numbers.
Isn't the partial sum 1/3 minus 1 over n plus 1? The second one.
I disagree. The first partial sum was 1/3 minus 1/4, which are three more than negatives.
But you're starting.
No. This is not the same as this. This is the number of the partial sum, not a reference to the number of the term. Yes.
See, that's just right.
I looked to connect this denominator to the number of the partial sum. There it looked like three more. Here it was also three more. So when it's in, it's three.
That's just
You just need to understand that n applied to this is the number of the partial sum. This is going to be an issue. You need to get used to it. And it's applied to that. Yes.
You would actually plug in 6.
To get S sub 3, you would probably have to have 5. Yes, that's true. Okay. Last but not least, did you have a little bit of trouble with the last one?
Yeah.
Okay, so you have to extend a little bit here. I will ask you to write in your notes, there's a little bit of a gap. In fact, I'm going to actually call it a big gap. Here's why. If you think 1 over 1/3 plus 1 over 2 minus 1 over 4. Wait a second, no collapsing yet. 1/3 minus 1/5. Hey, now we're starting to collapse a little bit after there's a gap. Plus 1/4 minus 1/6. The 1/4 goes away. Okay, so when there is a little bit of a gap between this number and that one, then the collapsing ones won't be right next to each other. They'll be a little stretched down the line. S1, for example, 1 minus 1/3, it's almost worthless. It tells me nothing. There's no pattern here. S2, also pretty worthless. 1 minus 1/3 plus 1/2 minus 1/4. Again, still no pattern. S3 is when the collapsing starts to happen. That's where I start to pay attention. At S3, I get 1, the third goes away, plus 1/2 minus 1/4 minus 1/5, if I take away. You want to focus where the collapsing starts. All right. S4, if I were so inclined, the thirds and the fourths go away, so it would be 1/2, 1 plus 1/2 minus 1/5 minus 1/6. Stop me if I made a move. You see? I think I understand the pattern now. I can write the partial sum formula, The partial sum is always 1.5, that's always there. 3/2 is fine. Then this, 1 over. Well, this next fraction was always what relation to the index? 1 over n plus 1. And the next one is always 1 over n plus 2. Yes?
That wasn't true in the first.
That's true because these were right next to each other. Plus 1 and plus 2, right next to each other. 0 and 1 are n and n plus 1 right next to each other.
Yeah, but like in the first two of this one.
Oh, yes.
It didn't have a 1/2. So
You're right. Okay, so that's actually a good point that I totally forgot in the last class. Does this rule apply to all n? If it only applies to some n from 1 and beyond, then you should stipulate that it's only for n greater than, actually, does it work for the others?
Yeah, because if you put an n of 1, the first of the one, minus 1 over 2, which cancels with the half.
Yeah, they do
So
work.
it does
Those
work.
work.
It just
Wow.
makes it look cool.
Wow, that's cool. Right on. Okay, so what is the limit of the sums then? 3/2. Okay. As n gets infinitely large, the n plus 1 and n plus 2 terms would go to 0, right? Okay. I might finish this on Thursday. We're running out of time here. This, would you just write yourself a note here? You must do partial fractions first to get a difference of sums. And how would you make this one a difference of 2 terms?
N plus 2.
Big log rules. Okay, so sometimes they don't make it all set up for you. Sometimes you'll have to decompose it first, okay? Okay, questions on whatever it is? 116. By the way, the test review is optional. I'll have it be posted online after school. Okay? There's a test tomorrow. Will you do well?
Yes.
Good. I'll be happy to help you prepare a 7th hour article before school tomorrow. Okay. 116 questions. 25. 24. 24.
No, I need to get my
Yeah, that is what she said.
17? 17. Twenty-five.
I thought you were like, I mean, it's just well, but like the next area. Oh, right.
Okay, 25. Okay, 25, the first thing I do on a trapezoid is to see, do the areas, are the subintervals the same? And looking at that table, all the subintervals are the same, yes? Okay, that means then that I can factor out the height of every trapezoid, and I'm going to call the integral roughly equal to the height over 2, and the first will be f at 2, and it only happens once on the edges, but the next one at 2.5 is part of both trapezoids, so it's going to be 2f at 2.5, 2f at 3s, 2f at 3.5s, 2f at 4s, and I have no idea whether this goes to 5, and a single f at 5. Right?
Yeah.
Okay. Is that, did you go, what's the height each time? A half, yes. So this would be like a fourth of all those. F? It's the y values of the table. They say y equals f of x. So go to the table and say something like 2.7, 2 of the next value, 3.5. 24. Question on 24. Okay. Y equals 1 over root x minus x, natural log of the absolute value of sine of x. Is the question about how to take the derivative, or why doesn't my answer look like theirs?
Why does my answer not look like theirs?
Your what?
My question is why does it not look like theirs? But
Oh, gotcha.
I could also be wrong too. So
Let's stay with the first. Let's just check your derivative and then not worry about that does it look like theirs. So this seems like it'd be negative 1 over 2 x to the 3 halves. Power rule on x to the negative 1/2. Let's go here. Maybe I'll write it this way. Negative 1/2 x to the negative 3 halves. Yeah?
what's the what thing?
Oh, that's a good question.
With the sign, right?
Oh, because it's
What is it called? With the squiggly.
Yeah. So that's a good question. Maybe you've gone
Piece-wise.
too far. What's the derivative of that?
and they're like hold on. What are the numbers?
Yeah.
No, it's like
Do you have to do all that absolute value? You've been doing this for 40 seconds. And so, no, you don't have to do all that absolute value stuff. For log, it works. Okay.
So for the arc sign of x over 2.
True. Don't need any piecewise. So the arc sine of x over 2 is 1 over, generally it's square root of 1 plus blank squared. But here you're going to have a chain rule. So besides that, you're going to have to multiply by.
Okay.
Okay?
Wait, isn't that 1/4?
Chain rule?
Oh, never mind.
Oh, yes, 2 7 sure.
Yeah,
Sure.
me too. I need to. Oh, wait, can you require me?
1, 2,
Wait, is it full?
4,
Yeah, it's full.
5, 6, 7, 8. Ay, ay, ay.
You just want me to turn it in now and then?
It's
It
up
starts
to you.
absent.
I can give you money, but I can just let you know if she's willing to get any more. I'll check to see if she has it.
Yeah, that'd be awesome.
It's on. Unless we say, I say, I think we can shut it.
You meet me in like 3. Not every time.
I just think this
Give a little bit more credit to his game. Sometimes it's like 6 or 7.